I think it's time to start. So, we are entering our first afternoon session, and we will continue in the ASR day. So, my pleasure to welcome Igor Szoke and later Karel Vesely. Both guys are senior researchers in the Beauty Speech and Fit group. Igor actually is mainly working on speech recognition, spoken term detection, and data augmentation, and he worked on several important projects here, mainly targeting ASR in the aviation domain, like air traffic control versus pilot communication. And now he is managing the project where we are asked to deliver an ASR system to the European Commission for the use of European services and some European companies. So Igor will be the first to talk. The second one is Karel Vesely, who is also a senior researcher here at BUT. He is one of the main co-authors of the famous CALDI toolkit, where he contributed especially an NNet1 module that at some time was really widely used. So this is Karel. And Karel also worked in a couple of important projects, including the American DARPA REDS, ARPA Babel, ARPA Material. Also, he was quite involved in the multilingual training of ASR models in the times where multilinguality was almost a vulgar word. And he's the chief developer in the European Connect project. So I think we will have a nice combination of high-level overview by Igor, like what it means and what it also means legally, and to deliver an ASR system. And then with Karel later on we will delve in details. So guys, here I stop and I give it to you, and thanks for agreeing to speak here.
Okay, hello, am I heard well? Okay, good, thank you. How was the lunch? Good, okay. So, well, this is kind of high-level presentation. There is zero mass equations, so sit down, relax, and you can listen how some ASR delivery project can look like. So, if you are a researcher, well, the life is usually fine. You are doing research and training something, writing papers. But later in your career, when you end up in some SME or in some company, it can happen that a customer will come and then some serious work or some funny or maybe some difficult times become. So, in our case, it was European Commission which asked us, or there was a tender, and we won it, and they asked us, okay, well, we need kind of European ASR solution which supports streaming and batch processing, and it's very good for low resource languages and can be scalable and modular. And as it is low resource languages, you will need some data for that languages. So you will collect the data and train the ASR on this data. Okay, looks interesting. So we start to communicate about how the solution should look like, and there are several options. The first thing you will think about, this is not about for the ECA, but overall, if you are in some SME and you should provide some solution, okay, the first thing, or in a startup, the first thing you will use is, okay, I buy some software as a service. Yeah, just go to Amazon, pay something, get the API key, and use it. This is good, it works, it's scalable, support, you have really quickly install it. There is the problem, maybe it's not the problem of the costs, but it can be also plus because the costs are pretty set. You are paying as you go, for example. You can have some problem with accuracy if you are really going to some niche language or niche topic, or I don't know, some acoustic channel. But maybe in the future you will lose some freedom. So it looks like that. You are sending the data to internet, to some service. They will give you back the transcription, and you are done. But what can happen, and it also happens time to time to us, that some company comes and says, okay, well, we are not happy to sending our data to big tech. Yeah, we want something on premise, something local. Yeah, so then you move on. Okay, so let's grab something which is online, already done, which is open source, already done, and use it locally. This is Whisper, yeah? So this is the second step. You just download Whisper, make it running. You get some freedom, you have it quickly, but there are some indirect costs because someone has to support it and you have some costs with it. And you can get not always the good word error rate. Yeah, so you download the solution and run it locally. So what happens if you have really some special audio channel? This is example from ATC communication. So you have, let's say, this audio.
Rider 4 Zulu, descent to altitude 4,000 feet, QNH 1008. 4,000 feet, QNH 1008, Rider 4 Zulu.
Or this one.
T1 Hotel, ground taxiway Echo 7, cross runway 16, taxiway Lima to hold short runway 10.
You send it to Whisper. And you get this, which is absolutely correct, absolutely useless. Yeah, because the Whisper output ATC is talking to the radio. Okay, yeah, it's true. Yeah, but you want the transcription. You don't want the information that ATC is talking to the radio. So then comes the time, and you are in the next step. You need to fine-tune, yeah, because you have really special data or some niche language, and the Whisper is not, or the open source solution is not good enough. Here, okay, it's starting to be interesting because you need some data, you need some knowledge, you have more costs, you need to do the support next. So then it's look like that. You take, for example, in the case of Whisper, you take the pre-trained model, you have some data, do the preparation, fine-tune, and then deploy. And this is you, right? This is your role here to make it run. And finally, maybe you can go even further and say, okay, I don't want to use any pre-trained models, anything like that. I will build it myself from scratch. This is also a solution. So then you need even more data, even more knowledge. You need some GPUs or maybe lots of GPUs. And then you are building everything from the scratch. So after discussion with the EC, the things come a little bit clearer. Yeah.
What does FOSS stand for?
Free open source software.
Oh, I see.
And it come out that we should make it built on pre-trained model, and it should be pre-trained all the EU languages, and we should train it. Yeah, so it start to be really nice and, well, challenging. So we want to build ASR for low-resource languages. What we need? Knowledge, some architecture. We need to know what to build on, tools, model, data, hardware, and some time to train it. Knowledge. You are here on the right place, JSALT summer school. So after JSALT summer school, you can do it. Architecture. As the solution should be deployable, scalable, it's not a good idea to just grab some Hugging Face pipeline, put the model there. It's good for some demonstrators, but not if you want really to scale it in some larger way. So that's why, well, you probably want to split the whole solution into something for the training and something really for the deployment. It should be lightweighted, easy, you can scale. It doesn't need so much GPU or CPU. So let's talk a little bit quickly about the runtime. I will not go really deep here because we are here on the speech summer school, but maybe it's good to know that there is something beyond, right? Just the component, which is this, the ASR. Yeah, there is something more. So we based it on some gRPC communication, which I think is quite fine. It's supported in Python, so if you are used to work with Python, it's very easy to create such modular architecture, then the communication, real-time streaming communication among the blocks. You can very easily support several clients, so one client can send some audio, another some video. There is you want to do some conversion, ASR, and then you do some post-processing, send the results back. Although it was quite nicely scalable, we just put here some Nginx load balancer there, and you can support easily a amount of clients, and it will do the balancing across the Dockers with the solution. Okay, this is just for understanding that if your solution or your ASR should be robust, you would need some pre-processing of the data. So if someone sends audio, video, whatever format, you want to extract the exact PCM format you need for the ASR, then do the transcription, you get some tokens out of it, and then you want to make some token post-processing, make words out of it, or even, and then format it to, let's say, JSON or Microsoft Word or whatever format you can imagine. And what's good that you can implement here some of your own modules, do some summarization, whatever, just put the communication into it, and you have even better solution. So let's more talk about the ASR, and especially after me, Karel Vesely will talk more closely about this, how to implement or how it's done. And now look about the training, which will be the rest of the presentation. So for some integrator who will use this solution, usually you don't want him to pre-train a model. Yeah, this is quite difficult. You need lots of resources and knowledge. But the fine-tuning can be something you want the integrator to be able to do. Just grab some data and very easily adapt the model and then deploy the model into the runtime. Tools, what to build it on. So we started to do some research, look around what tools are available. And of course, probably you want to use some tools which has some support, some community, and it's very easy, it's well known, and it's easy to build on top of this. So actually, this table is a little bit old, it's two years old, so maybe I'm missing some new tools. What we really went for is that we need large community, because if there is large community, it's a chance that the tool will continue to be here for 5-10 years. And what we desperately needed was the streaming, because this is one of the features of the solution. It has to be really streaming, with low latency, about half a second. So what we ended up with for the pre-training, we choose Hugging Face transformers because of the community, and of course because we had some experience. And as we do some research about the data, we knew that we will need to pre-train on about 500,000 hours of data, which is not really straightforward. Not all tools can do this really easily. For the runtime, we choose the K2 Sherpa ONMX because this tool is really lightweighted and well prepared for deployment. Yeah, the guys from Xiaomi did this very well. So it was, again, no-brainer to go with this. And fine-tuning, okay, we need to find out some way where to meet because we have two different tools. So let's go on, model. Today, it's easy, right? We have end-to-end models. We just need some audio data, some transcription. This is the end-to-end model. We train it. Okay, everything is easy and nice. To make it really working and with good word error rate, the thing is that the model can have some problems, or not the problems. In the machine learning, of course, the model has problems with the irregularities. So as it learns the patterns matching, if you have some irregularity, the model has to learn it. Yeah? And in the case of ASR, it needs to learn the pronunciation to writing irregularities, which for some languages is easy, for some languages is not. You can complicate it with the speakers, with environment, and so on and so on. Okay. So this is just to be aware of. You probably know. If not, it's good to remember. We have 3 languages. We worked for Czech, for Greek, and for Estonian. And if you don't understand Czech in the top here, that will be part of your life. Yeah? Maybe you will sometime train some ASR model for language you do not understand. Okay, there are some letters. You have to somehow cope with that. So for Czech has some very nice property. By the way, there are more of such features in the language, but this is this I, and there is Y and Y. Yeah, and it's pronounced E. In both cases, E. Yeah, so it's the same phoneme. But if there is masculine object, so then it's I, and when there is feminine, it's Y. Yeah, so men did, you write I, and women did, you write Y. This is not big deal as it is really close, but what in Czech you can do, that you can write a verb, many words, and then you write the subject. And according to the subject, you need to have correctly the I or Y here. And it's starting to be challenging for the models, yeah, because we have long sentence, and if you really want to have it right, the model has to look for the whole sentence for the really long context to do that. Yeah, there are some other things the model should catch. There is some example from French, let's say. French is also in this weird language. So this is something you need to think about and took the model right. This is nice picture figure about this. This is from one of the latest from Shinji group paper. And here you can see they trained ASR system with various number of parameters. And on the x-axis you have amount of data, on the y-axis you have word error rate. And what you can see, this is something they call, this is the pronunciation, no, the pronunciation, it's the, I forgot it, it's pronunciation transparency, let's say. Yeah. And it means that you have languages which are kind of irregular, which is kind of English or Chinese, and you have languages which are regular in the pronunciation way, in the mapping of the pronunciation to the text, which is Spanish. And you can see here that for Spanish, you need way more training data compared, for example, to English. And this is the impact of the language you are working on. Yeah, so this is what you can take into account if you really start to work with language, which is not very transparent. In this way, you will get higher word error rate, or you will need really way more data. So let's go back. Let's make the end-to-end model a little bit more transparent, so it's not black box anymore, and we will split it to the encoder-decoder. So probably know, encoder encodes the audio into some internal representation, and then the decoder takes care of transcribe or converting the representation into the transcription. And for the decoder, you have actually now, these are kind of standard approaches. You have the CTC head, you can have the RNNT and the AAD. So the CTC is pretty simple. You take the output of the encoder and convert it into the phonemes by one or few layers. For the RNNT, you have something like some simple language model, because you have here a loop taking the previous output of the decoder of the head. So this model can see into the past somehow and work with the past symbols it generates. And this is the autoregressive autoencoder, which has the attention, and this sees the whole sentence. So as we can say, this is what is in Whisper, and this AAD is good for the example I show you for the check. So if you have the sentence and we have the last word, which can affect the first word into the sentence, AAD is good for this. The problem is that this is not streamable. It's quite difficult to make it really natively streamable. You have to do some hacks there. But the RNNT and CTC is pretty easily streamable. You just put the streaming segment per segment, or how to say, buffer of few samples into it, and it will produce you with low latency the output, the transcription. And the RNNT, the good property is that as it has some language model inside, looking into the history, it's much stronger than the CTC. So we took the RNNT because it's a good compromise. Next, for the encoder, again, you will probably need to do some research, look into the models, what are the different encoders, what are the different objective functions, and so on and so on. Actually, when we started the project, it's kind of every 1 or every 2-3 months there is new model out. There is new paper saying, okay, this model is a little bit better, that model, that encoder is a little bit better. So finally we have to just say, okay, we are taking this one, and there is no more time to searching for new and better. So we ended up for the runtime with K2, which is based on ZipFormer and RNNT. For the pre-training, we choose Hugging Face. But the problem was that ZipFormer was not supported in K2. Yeah, because K2 was for the runtime, we have to take it. For the pre-training, the problem is that ZipFormer in K2 was not supported for the pre-training in the large scale. So we switched, and then we decided, let's go for the Hugging Face for the eBranch former and best RQ objective. This also, the best RQ is good because it's fast. It's much faster than Hubert, and we needed it for a really huge amount of data to pre-train. So in the end, we have to find some compromise for the fine-tuning, and we decided to implement eBranch former into K2. And for the decoder, we went with the RNNT because the RNNT is very well implemented in the K2 ONNX, so it was just very good solution. So we have to do some coding, or Karel had to do. This is how it works. So here, the integrator, if take the solution for the runtime, this is for the streaming. So this is the K2 based streaming runtime. But when we have inside the Hugging Face for the fine-tuning and pre-training, we also decided, okay, let's support the Hugging Face runtime batch processing. So there are both options, but this is the preferable one for streaming. For the fine-tuning, the primary one is the K2 icefall, where we implemented the eBranch former. This is the green one. But of course, as there is already the K2 toolkit, you can use the zip-former, which is the native model in the K2. And it's a pretty good model. It's quite lightweighted and provides good accuracies. So you can use from scratch. If you train from scratch, you can use this. If you want to use the pre-trained eBranch former, you can go through the yellow one. And if you want to stay, let's say, use this solution and stay on the side of the Hugging Face to really quickly digest the new models and new architectures, you can use the Hugging Face tool there. Data. The question was, I'm repeating for the audience on internet. So the question is if we are using the on-device inference or no, or running it on server. No. We are. Well, EC ideally would like to have also the on-device, really the edge computing, the on-device inference. This is absolutely out of our possibilities here because it's another project to make this thing to run on some low power device or mobile phone. So the ONNX is running on the server. Everything is a server solution, and it can be deployed like software as a service. Yeah, so you take the solution, you have a Docker, the runtime, you run it on some server, and then you connect to it, so you have your own SAS service. Have I answered? Yes. Yeah, okay. So, data. Okay, we have end-to-end ASR models, so for data it's easy. We need some data, we train the end-to-end model. But to train end-to-end model, you need a lot of data. Yeah, it's not so good to, especially when training from scratch, to have really few minutes or few hours of the data. You need kind of lot of data. Yeah, compared to the hybrid system or hybrid architectures Petr was talking in the morning, there it was a little bit easier. Our problem is that, well, we are in the low resource languages and we don't have a lot of data. Yeah? We can have few hours, so we are doomed here. So what to do? Okay, let's pre-train. It's the usual approach. If you have many data or lots of data which are not transcribed, you can take it, pre-train the encoder to have very well-trained encoder, and then you use few samples of transcribed data to train just the decoder, and then you are done. So, well, there is plenty of data outside here. You have the whole YouTube, you read the papers, and one big tech is training on 1 million hours, another big tech is training on 500,000 hours of data. There is lots of data. That's true. There is lots of data. You can download it. But then you hit lawyer in your company, which starts to read the license of the data. And after he reads it, you hit the DPO, who takes care about DPR. Who doesn't know, this is the data protection officer who takes about the data protection record. This is very important if you are in Europe. If you are in US or China, probably you don't have such problems. And we were quite lucky that we missed the AI Act. So what's the issue with the data? Yeah, I'm here speaking for, especially for if you are really from Europe and you will maybe end up in some European SME. So if you want to create or train a model which will be provided freely or not freely to some customers and for commercial usage, usually the license of the data is not so straightforward. I think that YouTube, Spotify licenses are not very compatible with commercial usage of the models. The best you can do is to find CC0 data, or you can buy the data, or you can kind of bootstrap or collect the data yourself, but this is also quite tricky. And if you start to look for CC0 data, you find out there is not much of such databases. Yeah, there is Mozilla Common Voice, Vox Populi, this is the biggest one, and then you are probably done. Yeah. Another thing which is quite important is that the model you are training or you are providing to the others has to be transparent. What does it mean? It means that you theoretically should be able to track down any single training example to the human behind it. Yeah, because humans in this way has the rights that you can be kind of removed from the training data. So theoretically, if I say, okay, I am in Mozilla Common Voice and I don't want to be there anymore, I ask Mozilla to remove me, Mozilla sends email to all the people registered there, and you theoretically should retrain the model and remove my voice from the Mozilla Common Voice. So then you start to communicate with the lawyers and the DPOs, and another funny thing finds out, this is just kind of story, that our data as machine learning engineers, our data keyword is not their data keyword. Their data means name, address, age, ID, whatever. Yeah? But if we are talking to them, we are talking about data like, okay, I have database of this audio and transcript, so it's quite funny talk with them. Problem with the DP is that the training data contains personal data, which is voice and content. Yeah? Voice is the biometrical information, and the content is any kind of this data, which is pronounced, which is set in the audio. To make it short, it's good. Probably the best data sources is some public recordings, because if someone publicly talks and the talk is recorded, the person is aware of, okay, my data is going to be in public, so can be somehow used. Recording if you have some SME working in some call centers, if you want to record the calls from the call center of your customers, you are here in trouble because it's quite difficult. You need to have the consent. What is a good solution, or what we find out is a good thing, is that we find out a way, and we are saying that trained ASR model forgets the data. Yeah? So if you train ASR model, it forgets all of this data because it's not there. And also it forgets the identity of the speakers. Yeah, so this is one way how to get rid of all the DP. When you train, okay, the model is no more containing any personal data. Just very quickly, this is the GDPR. What's kind of important if you will train in your company? You have some purpose limitation, so you should use the data, collect the data just for particular purpose, not like, okay, let's collect it, and maybe the data will be handy later in 1 year for some other project. This usually doesn't work. You really have to specify it from the day zero, and if the purpose is no more legit, just delete the data. You should use only data you need, but well, you need only the voice and the transcription. you should store the data for necessary time, and this is the thing, the right to erasure, so right to be forgotten from the training data. So we have some data, let's say, and we need to transcribe it. As I said, the best source of the data for such project is some public data. Yeah, this is data coming from national parliaments, EC parliament, and so on, because of the public speeches. So we collected some data from these sources, and now we needed to transcribe the data, yeah, to have the transcriptions. So it's another quite interesting process. It's not like, as researchers, you maybe use that, okay, I download from Hugging Face this data set, and it's pretty ready, and just run the training. You have absolute mess downloaded from the internet, and you need to put it in some nice form for training. Here, a big thanks from Elda doing this stuff in the project. So what you need, first, your transcription should fit the task. So you should think well about what the task is. If it is ASR, for what purpose is the ASR, right? So how you would like to transcribe the numerals? How would you like to treat the speaker change? For example, when we were doing the ATC, in what format you want to have the call signs? Usually the ATCOs are used to have it in some just letters and numbers, not expanded into the words. Everything like that should be thought about at the beginning. So when you hire the annotators, you already know what the output is, yeah, what the transcription is. We end up with quite long transcription manual. This is just the topics you should consider when transcribing, how to treat spelling, punctuation, acronyms, truncation, mispronunciation. All of these things should be taken into account, and if you hire someone to transcribe the data, it has to be clearly described. And then, okay, you have some process of it, so you start with the data collection, collect the data, and what usually you end up is some bootstrapping, so you transcribe some part of the data with some publicly available ASR, let's say, give it to transcribers, then will correct the errors, you improve your ASR, transcribe more data, and so on. And using this, you improving your ASR and transcribing some data, unless you are okay with the amount of data you need. This is an example from the ATC project. So we had similar pipeline, and here we end up with the community. So we thought, okay, we will create some tool for the community, and people who want to learn, who want to be pilots or ATCOs, they will just use it to listen, to make them used to listening the ATC communication. This was this example I played for the Whisper. So you see, or you heard that it's quite tough to understand. So they can train, and by the way, they will annotate the data. Yeah, they will correct the errors done by ASR. So this is, for example, the pipeline, quite funny. So at the beginning, there was 26 hours of raw data collected from antenna from the air. Then some filtering was done, short segments, long segments were discarded. Then something with very high SNR was discarded because we are not interested in really noisy data. Something, if there was no English, it was discarded, so we took just the English. We then ran some ASR, and according to the confidence, we discarded data where the ASR is not confident, ended up with 0.6 hours of data out of 26. And then put it into the portal for the community, and we ended up with 23 seconds. So this way can work, but you need to have some community or someone who will really want to transcribe, and usually you end up with paying these people. So this is the output of the transcription data we collected. So again, it's Czech because, well, you can work whatever language. Just to emphasize, we put there labels indicating there is non-Czech speech, there is speaker change, considering the numerals, the numbers, this is some spelling, this is the date, the format of the date, named entities, so you want the capitalization here, but we don't want the capitalization at the beginning of the sentence because this can be guessed from the punctuation. So you ended up with something which has some nice structure, and you can start to train on top of it. For the pre-training, for the SSL, it's much easier. You just really can grab all the data from the internet or the data set you want. Just be sure that you have the right sampling. Your files are not too short, and your files are not too long, because you can end up with files like 15 hours. It usually breaks something in the pipeline. Too short files, it's really deadly for your file system. And there should be some speech in the data, usually. You don't want to train on noise or music. So, for the pre-training, we ended up, after considering all these data protection and licensing and whatever, we ended up with Vox Populi, Mozilla Common Voice, and LELD, which is the data set we collected. So only these two data sets we found out that is really useful in the European space for training and has good enough licensing.
Yeah, I just was wondering of the long audio files, because you can also process the audio files if they contain a speech, like you can segment. So you are discarding long audio files?
No. Yes, the question was that we can segment the long audio files. That's true. We segment it, but if the audio file is really, really long, you may even have issues while the segmenting. It can just get out of the memory. Okay. Yeah, so the thing is that if you have really long audio, maybe it's better just chop it, and then you can do the segmentation. Yeah, but really, if you download something from YouTube, you can end up with crazy, crazy data. For the fine-tuning, again, Vox Populi, Mozilla Common Voice. Here you can see that for example, Greek, you don't have any data in Vox Populi, and you have quite low amount of data from the Mozilla. And we collected 250 hours of transcribed data here from EC Parliament, National Parliament, municipalities. Yeah, this is the best sources according to the data protection and licensing constraint. So now it's time for heavy lifting, some training. We got Lumi HPC for 1 year for this project. The first thing, if you are in this such ranges or such scale of training data, the first thing you will hit is that HPCs overall doesn't like high amounts of files, which means that even you can't prepare the Mozilla Common Voice there, because for languages like English, if you start to preparing Mozilla Common Voice, it has to download in the Hugging Face. I'm talking about the Hugging Face. It starts to download the data set, and the data set has several million of files, and you will hit the limit, and you are done. Yes, so you need it to prepare the data somewhere else, not at the HPC. What's good is to use some formats for the data storage. We used arrows, but you can use HDF5, Parquet, whatever. The toolkit usually has it. The Hugging Face data set supports to exporting or packing the data set into such formats. So you end up with few large files which are very, very nicely treated by the HPC. Just for example, one Vox Populi language, the preparation took here at BUT for 2 to 5 days. Because, well, you have to download the data, you have to do the VAD, do the split, some conversion, and dumping to Hugging Face dataset. And this is not really quickly doable. Yeah, so just for you to remember, it's not, if you want to train something like that, you will not prepare the data in few days. It can take few weeks. You have 9 to 22,000 hours for speech for every language from Vox Populi. And the prepared data set, one of the language has about 2 terabytes in arrows. And during the preparation, it produced about 10 terabytes in the cache. So you can't parallelize this. There is 23 languages, so you can't parallelize to 23 languages because you just get out of the cache. Or if in your institution, if you have petabyte cache disk, okay, you can do it. We don't have petabytes, so I have to prepare several languages, delete the cache, upload to HPC, and so on and so on and so on. In the total, ended up with about 50 terabytes on the HPC, and the preparation took about two months. Before you do this, it's good to find out on the HPC the information about sharding, because it's different file system on different HPCs. And when you start to train, you would like to parallelize the load on the physical disk servers in their file system. And some HPCs may have some special settings which you need to set up before you upload the data so the file system does the sharding right. Otherwise, you will end up with a problem when training that it will end up on one or few disks and it will overload it and your training is not efficient. From the training perspective, well, we spent about 3 months of tweaking the code because Lumi has, the feature is based on AMD infrastructure, which is a little bit different to NVIDIA's, and in that time, even Lumi was kind of learning how to make their environment stable, so it was quite funny times. That we pre-train several tens of pre-training just to experimenting with hyperparameters debugging, you probably can imagine. We find out, we trained in the end 3 sizes of models, times, causal and non-causal. Causal means that the model is trained, that it doesn't look into the future. Non-causal, so it's for the streaming. Non-causal, that it looks into the future. So it's standard model with attention as you are used to. And, well, we utilize really long, days-long jobs. And you need to count out that sometimes you have some long waiting time in the queues. So checkpoints, checkpoints, checkpoints. Yeah, this is for the pre-training. True. Yeah, well, this is tricky, of course. The question was for pre-training how we test that we are on the right track, right, with the pre-training. Well, this is why we started the training. For about 1 epoch, for the small model, it took few days. So here, at the really beginning of the training, we just took, I don't know, 3, 4, 5 checkpoints after every 3 or 6 hours. And we trained, I will maybe talk about it a little bit later. We took CTC and fine-tuned with CTC, yeah? And as the CTC is really weak head, we expected that it will more reflect the encoder and what the encoder learned. Yeah, so we use CTC and just track the loss. We tracked the water error rate with CTC here. And if everything looks fine, we just let it run longer. For the small model, it was okay, and then we just expected for the larger models, hopefully it will behave similarly. Yeah, but so this is just this is the 80 million model training, pre-training. So it was 24 days on these 4 nodes times 8 GPUs of this AMD Instinct, whatever. And well, okay, we used loss. I will not comment this.
Is there a reason why the code book usage increases over time? Like, why does it stay like that? Because it's really high.
Well, here we implemented the feature, so we don't have it from. I don't have it here from 0. So that's why it's kind of this, but and this was implemented for the best RQ because we want to know what happenings behind when the training, if the code book is well utilized. So in the end, I think this was quite good indicator of if the model is really training or not. For the larger model, 200 million, here you have it from the first epoch. Yeah, so it does something like that, but it's still in very nice range, so it looks like it's working. And it took 54 days. We hit, for example, we hit a problems with the 600 million model where we needed to train it on 8 nodes, and here the training start to be unstable. And I guess it's because we just hit some limits on LUMI. Yeah, too much reading from the disks because the jobs crashed quite frequently. Okay, I talked about this. Yeah, so we measured water error rate, character error rate using CTC every 1 quarter of epoch. So some results with respect to the project. Yeah, so just to summarize, this is the pre-training amount of data, all EU languages, encoder eBranch formula with best RQ. For the fine-tuning, about 300 hours of target data. So this is some EC parliamentary talks, Vox Populi, Common Voice, and decoder CTC, RNNT, AAD. Metrics, word error rate, and mapped word error rate. I have it in some results. What does it mean? The mapped word error rate just reflects or doesn't count on things like if you have different way of transcribing the date, the time, it doesn't count into the capitalization and punctuation, for example. Yeah, so it focuses more about the content, not these things which people, if you read the transcript, do not care also about. So the main comparison, so here the blue one is the vanilla whisper. Yeah, so if we take the vanilla whisper, the base, small, medium, this is the whisper sizes, and we try to map our models to the whisper model sizes. So if you took whisper and decode our test set based on our target data, we ended up with this word error rate. So this is for the base. It's for the check. It's quite unusable. Yeah, you have 80%. You can, of course, fine-tune the whisper. So you get somewhere here, which is not terribly bad, but still, I think, not useful. And here the other colors are the models we trained. So the yellow one is our pre-trained model with CTC. The green one when we went to the RNNT. I will have one more slide with that. And this is when we switched to K2 fine-tuning of the E-branch pre-trained E-branch former, so from green to this, what is it, orange. And then here is if we train the zip former from scratch, I think. I don't know why there is no streaming. So it's even a little bit better. Okay, this is something also I think worth considering mentioning. Here is the comparison across languages and across the decoder type and the use case. Yeah? So if you go in the numbers from left to right, you have different use case, which means non-streaming to streaming. Yeah, non-streaming means batch processing, so you have audio, 1 hour audio, throw it on the decoder, and then you get the whole transcription, and you allow the ASR to see the whole recording. While the streaming just works in the real time with low latency, and it can see just the history, not the future. So you can see that you are usually missing some few % of the accuracy, given by that you can't see in the future for a longer context. And where going from CTC to RNNT, you can see that it's from the top to the down. You can see that you get some improvement when you have the stronger head or stronger decoder with the history. What happened with the training data? So here is a graph of when we started to train on 1 hour up to 250 hours or 300 hours. So if we trained from scratch, non-causal CTC models, so if you have 1 hour, you are not able to train such system at all. Yeah, from 2 hours, okay, it does something, but it's really start to work somewhere about 50, 100 or more hours, yeah, somewhere here. Here you can see the gain from the pre-training. Of course, the encoder saw already some speech, so it starts in some maybe reasonable, especially the non-causal version, in some reasonable word error rates, good enough for some bootstrapping, and then goes to better numbers. Okay, nice, check. It's nice, but it's not much important for people. You want to see some results from the English. So this is comparison on the English. And okay, I don't have these numbers here because due to some data protection, again, stuff, we were not able to process this data, so we just processed the Vox Populi. So I have just these numbers. And so this is the Whisper, not fine-tuned on the Vox Populi, has 8% word error rate. XLSR models, this is, Alexei, this is E-branch former, right? Vanilla transformer, okay. So you can see here vanilla transformer with these sizes of the model CTC fine-tuned. This is the amount of data trained on. So here you got 30 to 8 word error rate. The green one is our model. So here we have kind of similar training data, similar size of the model, or a little bit smaller than this one, and we are about kind of the same word error rates. And decrypt, this is what Alex trained. I don't know if you will talk about this. No, you will not. Next week, okay. So this was trained on quite huge amount of data of the English, and yeah, it very nicely outperformed the Whisper. So if you want to have some more discussion about the numbers, we can do it then offline. What was interesting experiment was for us was also to compare the multilingual pre-trained model to monolingual pre-trained model. Yeah, because in Czech we have this one. This was trained by West Bohemia University. It's kind of two years old. This is the CLTRAS. And in another project, we trained eBranch former model just on English. Very similar setup to the pre-trained model we were training for the EU. And this one, the red one, is trained on 80,000 hours of Czech. This one, the pink one, is trained on 70,000 hours of Czech pre-trained. So here you can see that, well, the European model is a little bit worse than if we just pre-train on much more data, much more Czech data, yeah, because the EU models saw about, I would say, 25,000 hours of Czech. Yeah, this one is about 3 times larger for pre-training, three times more pre-training data. And there is some gain. Yeah. The WEF-to-WEC was significantly worse than the eBranch former here. So this is, again, maybe one thing you can consider if you are really in a monolingual scenario and you have lots of data for pre-training. Maybe pre-train on the target language is also a solution. So that's kind of all from my presentation. So to conclude, well, all the models, the data, the code base will be published soon by EC. Actually, they are in some process of internal publishing and other stuff, but should be published. So especially for people from EU, you can then use it. It's multilingual EU model pre-train with some code base based on Hugging Face and runtime, which should scale, so can be handy. Okay, well, as expected, more data better. If you have some really good amounts of training data, maybe training from scratch can work also. Depends on the pre-training is good for if you have a really small amount of the transcribed data. What we find out that the richness, where the complexity of language doesn't matter, but the orthographic transparency matters. Yeah, this is, I think, quite important, yeah, the irregularities. And, well, also the application matter because it really depends. If your application is some simple ASR, you will probably go for a different solution that if really need complex multilingual ASR. And the last thing also is timing, which means the global timing, because when you start such project, you go inside, you select, you do the research, you select the models, everything, and maybe after a few months, some very nice new model appears, and then you think, okay, should we switch? Should not we switch? Well, probably not because then you can't make it on time to deliver the project, but now it's quite interesting times because there is so many new models every month that it can be difficult to really select the good one with the vision that in 5 years it will still work and it will be relevant. Okay, that's it. Thank you. If there are questions, I can answer. If I know the...
Just one question. What your test conditions or the spontaneity and the far field, is it far field and spontaneous, your test condition?
The test condition was for primarily for EC parliamentary speech, so it's not far field, and I would not say it's very spontaneous. So it's rather, it's the parliamentary discussions, right? So you have good audio quality, and you have the speech is not very spontaneous. Well, there are not much of the speaker overlaps. What's there in the data? What is interesting that there are the interpreters, which means that if you have the audio, you have French, blah blah blah, and then you have switched to Czech because the interpreter starts to interpret the French guy and starts to speak in Czech. That's why, if you remember, there was the LNG token in the transcription, which should really catch out of language or the non-Czech or non-Greek data, because it very often happens that you have different languages in the audio, and we wanted to cover it, but this token that there is non-Czech speaker change and then starts the Czech. Yeah, maybe. I'll show it. Also, well, one of the things was that they would like to have there some diarization or speaker turn detection, but to provide streaming diarization, it's another such project. Yeah. So what we decided to go for is to put into the transcription the speaker change, and let the ASR to train to learn. Okay, there is change in the speaker, so I will indicate it by this token. And it's not diarization, but at least we can do something with that, like make a new line and indicate, okay, there is switch of the speaker.
How much computing power did you have to train everything?
Sorry?
How much computing power did you have to train everything?
How much computing power did you have for everything? I think we had 50,000 node hours of Lumi.
I mean, like, on what hardware?
Hardware. Sorry?
What hardware did you use? How much hardware
GPU? How much or what hardware? I don't.
How many GPU units? What kind of GPUs? Stuff like that.
AMD. It was in Lumi HPC. So it was this one. 4 nodes, 8 GPUs, and 54 days.
I have a question about the best option for training. Since you increase, like, compared to the, as I guess, base model that's trained on every speech or very simple, how much did you have to increase, or did you increase the codebook size? Because obviously, since you have a lot of different languages, you might have more fine-grained or a lot of different acoustic units to predict the quantizer. So did you have to change the codebook size, or how the quantizer behave, or did you keep it?
We did some simple experiments. With the question was about if we change the codebook size. We did some experiments in that matter, but we haven't found this to be, according to the size we had, to be really the issue. So we stick with what was officially proposed by, and I forgot who. Four. Four code books. Four. Yeah, so 4 code books and 10,000, yeah, 1,000, the size of the code book. And it was pretty stable.
At the very beginning, you mentioned that the prerequisites for this project, you don't want to be sending off your audio to a model, and you're, correct me if I'm wrong, like you're encoding into some form, you're sending that out to the inference, and then you're receiving similar encoding, and then you decode it on your end. How is that? Is that okay in terms of, like, if they don't want you sending audio, but you're allowed to send encoded, like to the inference model, if it's not being, because you're not running the inference model locally, I would think.
Sorry, I don't understand.
So
Yep.
I understood, like, at the very beginning, you said you don't want to be sending off audio to an external,
Yeah.
for it to be transcribed. So instead, you're having it encoded, and you send that encoded result to your inference model, which is external, but only that inference model is understanding that rather than you're sending raw audio. How do you like specify that difference? I guess it sort of comes down to like permission in terms of like it's okay to send the encoded, but it's not okay to send the just straight audio. Am I understanding that correctly?
We are talking about these figures or this one or about here, this one?
Yes. Yeah, so instead of sending it.
Well, in the service, the question is if we send in the audio or encoded audio or, yeah. Well, the service is implemented, well, to be, everything to be, you know, encrypted. The gRPC is, can be encrypted here. Yeah, so what you can, it depends on you. Yeah, but it's easy if you generate the SSL keys, you can encrypt this communication, and if you are too paranoid, you can encrypt also the communication inside the Docker. It was quite straightforward. So it is possible. It depends on the integrator if it wants to use the encryption or not.
One question maybe related with this, like just because the models are not too big just to make inference on device, so it would be possible to make inference on device, which is with these architectures based on SIG formers or branch formers, or is there any problem with the architecture that you cannot use the model to infer on device?
Well, this is more question for Karel, but I think that the Sherpa ONN mix should be portable to device, right? It's
there is support for Android, also for iOS, and for HarmonyOS in Sherpa ONN, so in theory it should be.
But it is linked with the architecture, because I know that Sherpa works with this NCNN kind of architecture, which is not based on SIG former or
You don't have wirings to many different environments and technologies there, so but you
maybe Karel will now talk, so ask it again, and he will have the mic, and guys from YouTube can enjoy also the answer.
Yeah. Okay. Hello. Let's start. Honza already introduced me. I'm Karel. I'm the apprentice of Lukáš Burget and then Pouvi. Also, partially, I was involved in the Kaldi project. Now there is the new generation, the K2 project, and we used it for the EU ASR. We based it on it for the deliveries. So the second part should be more technical. I chose some technically interesting aspects of the work which was done. So let's start. First point is, in the abstract we promised that we will compare the pre-trained models with the model training from scratch. And the playground for us at the time point we were starting the project, there was Alex who just implemented the eBranch former encoder model and started getting very nice results from it. At the same time, I was playing with K2, training first zip former RNNT systems. So, the setting was that we were supposed to deliver a system which would involve also pre-training of the encoder. And encoder pre-training was not implemented at that time point in the, let's say, in the K2 technologies. So we explored both these tracks. So the eBranch former model, it's using the Hugging Face transformers library as the backbone. It's the conformer model, which is like the original code, which was then some modules were re-implemented to the eBranch former model. And zip former, it's also, it has some roots in the conformer, but there was some video from Dan Povey where he explained what the differences are. I will touch it a little bit, but he's the the best person to describe this model. So I will just maybe refer to some interesting points, but yeah, I should not speak for him or in any way. Yeah, the important aspect is that both encoders they now support the chunk-wise streaming ASR, which by itself is technically challenging. And for zip former, the support already existed in the code, but for the eBranch former, we had to do it ourselves. So we had to take the encoder, adapt it for the streaming ASR, and implement the fine-tuning routines, the inference routines, and make sure that everything works. So I'll start with the technical description of the eBranch former model. So here is the link. You can read later on if you are interested in learning. So basically, it's the branch former, it's encoder, which has some front end. In our case, it's FBank features. Then there is some convolutional subsampling. Usually, it's like a cascade of 2D convolutions, which creates the very input of the transformer block inside. And the branch former block itself, well, there are several of them, but each has this internal structure that there is some module called global extractor, some other module in parallel called local extractor, and there are some merging module plus some normalization, and there is also this residual connection parallel to that. So yeah, the important part is this this internal structure of the block. In conformer, it's the other way around. That here it's in parallel. This global extractor and local extractor, and in conformer they are serial. So the global extractor, this is just vanilla transformer module, which means it has the self-attention mechanism inside of it. So the module itself, there is multi-head attention and then some multi-layer neural network inside of it, plus the residual connection. And this multi-head self-attention, well, this is taken from Bishop mostly. So the attention mechanism, I think Peter Schwartz introduced it in the morning. For self-attention, the important aspect is that the queries, keys, and values, all of these comes from the input of the module, and they have these independent linear transformations to get these QKV matrices, as shown here. And then the attention mechanism is about calculating these attention scores, which is like, we have, well, in attention, all the inputs are linked to all the outputs, and unless there are some masking involved in it, and there are the attention scores, which are like, how to say, the output from the attention is like weighted combination of the inputs from the V matrix, and how the weights are, this is by the attention scores, which are from this branch of the computation. So you can see it on this formula that there's the Q matrix, key matrix, and they are multiplied together, normalized with the dimensionality. Optionally, there can be some masking at it. So if some time points should not be attended, some very low number, like minus 1E9, is added into it so that the attention weight in the end becomes negligible, well, it's hard zero, and that's it. And so this is a single attention, and in this multi-head self-attention, there are several such attention modules in parallel, and that's it. So this is the global extractor. The local extractor, there is some convolutional spatial gating unit inside, gating unit. So what this, it includes inside 1D, well, this depthwise convolution is implemented with 1D convolution, which is done just over the time axis. So the time span is like 31 frames, where each time step is 40 milliseconds in this case. And you can see it, so there are some modules before and after. If we focus on this CSGU, here are some like signals coming in. There is a split, so half of the signals is used for this direct wiring, second half is used for this branch, and inside this branch there is layer norm and the depthwise convolution, so it's, each of these signals has the convolution applied on it. Each channel of the signal has its own weights, and the output of the convolution depends on the convolution weights and the input. And if they are similar, it emits, there are some non-zero values coming out of it, which are then used to like multiply those directly going signals. And in the other case, if they are orthogonal, if there is no similarity between them, it's just there should be close to zero output, and it should then sort of disable these direct links in this multiplicative node over here. And it's called, global extractor is the transformer, because everything is linked together from the beginning to the end of the, let's say, sequence, the utterance. And here it's local extractor, that the context is limited by the length of the convolution. So this is the second module. And the third one is the merge. And before eBranch former, there was a branch former network, and the difference between the two is between this B and C figure, that originally there was just concatenation and linear transform for joining, and the eBranch former came with like another pointwise convolution. But the previous one was multiplicative, and this one is additive. So again, there's some signal, there are some weights, and if they are similar or dissimilar, based on that, something is added or not to the signals, to those direct signals which are over here. So
what was the main reason for switching from the usual conformer with the statue to branch former? Like faster, or?
I think it was giving better results. There was a paper published where they compared with conformer, and it was, yeah. And for best RQ, it's, it depends what is compared with. For best RQ, the idea is that there is some like predefined distribution of the data, that the data is assumed to have zero mean and unit variance, and then best RQ works for this condition. So best RQ, what it does, it generates a random linear projection to some subspace, and then inside this subspace, it also generates some random vectors in the space which should cover well the data. But everything is stochastic, and it just assumes that the distribution of the data is Gaussian, and it doesn't need to like visit the data like compared to k-means. K-mean is iterative algorithm which starts from some initialization and then updates the centroids to get the code book, but this is just totally random. But yet it works. Then there is this training classification into those units and hiding some inputs and doing the reconstruction training. And so it's, so there it's, the speed is very good for best RQ, and also in the paper they had compared to the other techniques and shown that it works well. Yeah, so ZipFormer is the second encoder we worked with. So this one has a little different internal structure. So what is special here that it's like this U-network-like architecture, so that the frame rates inside these blocks of components, the frame rate then first decreases and later increases. So each block processes the data with different, let's say, precision of the input, but yet there are these residual connections so that the original resolution is preserved from the beginning to the end. So there are these downsample and upsample units, which in speaking PyTorch is just averages few frames, does some processing, and then like repeats frames several times. Plus there are these bypass connections, so that, I'm repeating myself here. And inside the blocks there are also some other bypass connections, so it's quite complex that there are many different crossroads to how the data flows through it. Concerning the front end, in ZipFormer, there are the FBank features. It's standard, what was in Kaldi, these high resolution features. It's the same thing as before. There are no normalizations. And inside this conf embed, this is the pre-encoder. It contains, there are 3 times 2D convolutions and something called conf next inside of it, but there are other components inside as well, so some activation functions, but there is also balancer, which like tries to shift the activations to like prevent some pathological cases. Whitening, which tries to make the signals orthogonal to each other. It's by some loss term. That's how it's done. Bias norm is like some special variant of layer norm, which is used in ZipFormer and dropout. So now let's have a look how the zip-former block looks inside. So in the presentation I saw it's like pretty much 2 conformer blocks in one. Is a single zip-former block. And so you can see there are some 3 feed-forward networks, this greenish 3 attention modules. So there is this one, and this nonlinear attention, yeah, this one over here. And some convolution modules inside. Yeah, what is like new in zip-former is this reuse of attention weights. So this attention matrix is computed once, and then it's used 3 times. And so this computation over here is done just once, and this saves computation, both for training and for inference also. And yeah, I'm not going into the like very core that these modules have further like some internal structure, like these feed-forward networks, convolution networks, but just to give some notion of what zip-former is. And there is also this nonlinear attention. This is also new. So there is this attention matrix coming inside. So this is this arrow, there's this attention weights. And you can see that there are like 2 gates surrounding the attention. This is single head attention mechanism over here inside. And there are 2 gates, 2 multiplicative gates. One is to the entrance to the attention, and one is to on the exit from the attention. Yeah, don't ask me about details. This is how it is in the model. It works very nice. That usually Denpovi, he has. It's not easy to understand what he does, but usually it just works. You can call it white magic, I don't know. But, well, that's my view. Here, in this section, this is more for the reference. There are some zip-former tricks inside. There is, in the usual system, there is ADAM-W used as the optimizer. In zip-former, there is scaled ADAM. And in the documentation, they say that it's like as if there was some scalar applied to the model parameters, and there is gradient applied to this scalar, so that at the beginning of the training, it's sort of like shifts the parameters so that they get to the dynamics where it should be according to the data. So this is compared to ADAM. There is this term, which is new inside this update rule. Next, add-in scheduler. Well, this is maybe not that much special. Any training needs some learning rate scheduling, and this one is parameterized both by number of training steps and number of epoch, so that it works reasonably for like smaller data sets, but also for bigger data sets. Plus, there is some warm-up at the very beginning of the training, which like linearly increases the learning rate, but yeah, that's not, there is bias norm. So in the normal layer norm, there is this like length normalization. There is some layer, it is some vector in some direction, and by normalizing the variance, the length of the vector just gets like normalized. And empirically, they saw in Xiaomi that there were some like neurons where there was one big activation and some other neurons, and it looked like this big activation was there to just like disable this length normalization, so whatever rest is there can flow through the network. So they try to like allow this by the model already, that there is this bias norm, there is this B vector, and if it has 0 parameters, it does the length normalization. If it learns some higher values there, it just disables the length normalization. Plus, there is this gamma over here. They saw that it can happen that it flips the sign from 0 to 1, then the gradient goes in the opposite direction, and this is bad for the training. So to avoid these oscillations, they put this exponent over here, and then this sign flip no longer occurs. And yeah, and compared to, like, let's say, conformer, there is just one instance here of the layer norm. So there is much less normalizations compared to conformer layer. And this is like 2 layers in one. Yeah, the activation function, again, something non-standard. There is this swoosh R and swoosh L, depending on these like crossing points. Either it's the left one for this green, or the right one, which like goes the 0 crossing point for this orange. And the formulas look like numerically identified, but yeah, the performance is about the same as with the swish, so why not? Plus, there are other modules like, yeah, what seemed important is this learnable bypass, that at the very beginning, the bypass was nearly switched off for first 20K steps. So it was restricted to be 0.8 to 1.0. And then it was sort of relaxed so it can learn to like, yeah, use the bypass for the signals. Yeah, whitening, I spoke about it a little bit, that yeah, there was this semi-orthogonal TDNN. It's the same idea, but here applied for zip former. That was in Kaldi already. And balancer, yeah, try to avoid like neurons in pathological states, so that it can, most of the time is disabled, but if the neuron misbehaves, there is some loss term which pushes it towards the healthy area that, yeah, that the mean absolute value of activations for a neuron should belong to some interval. And also, yeah, there is some like recommended rate of having positive activations. The neuron can have both positive and negative activations, but if it's like always negative, it's a bad sign that it's probably doing nothing useful. Okay. So this was, yeah, those were the heaviest slides. I'm not like explaining everything into detail. I don't feel like myself to be like good for that, but this is for reference that such things are in K2, and yes?
Does ZipFormer work well across different data sets? Because this seems to be that they have carefully tweaked everything. It's all engineered and
from what I saw, it generalizes quite well across data sets. That, yeah, it also beats these pre-trained models, so it should most likely it's quite efficient. And I saw that, yeah, I will spoil part of the presentation, even for small data sets, not as small as for WAF2-VEC2 models, like 1 hour training data, that's already too low, but already with some smallish, like tens of hours, it can already train like to some extent reasonable ASR. So ASR training. So I've described the encoder models. So encoder by itself, it just cannot do ASR. It's just like producing some embeddings. And to make ASR out of it, either we put their CTC head and train with CTC loss, and it becomes the CTC ASR system. Or if we are interested in having transducer ASR, so those are now very popular for like mobile phone applications, or even, well, the main K2 system is transducer, giving the best results, which is also supported for the deployment. So in this case of transducer, there is the predictor module edit. This predictor, it's getting the previous output symbols. So it acts a little bit like n-gram language model. So it remembers 2 previous output symbols and provides some embeddings to represent this context. And then there is the joiner module, which gets the inputs from encoder, from the predictor, and generates the posterior probabilities over the set of tokens. For the transducer, it's still time synchronous, so every, let's say, 20 milliseconds, there is some distribution over the labels, and the decoder just searches paths in this. But yeah, so this is transducer. Well, for K2, it's not just vanilla transducer that is in PyTorch, but it's something, let's say, adapted or improved. So there is this pruned RNNT loss. Well, in the old times of Kaldi, there were lattices, and we were using pruning to just make them less deep and to accelerate the processing. And so similar idea is used for the transducer training, that there is some trivial joiner network, which is fast to evaluate. And from this step, there is, for each time frame, there is a list of n like tokens, which are likely to appear in the output. And then there is this full joiner network, which is then used for the precise search of the like final hypothesis of the neural network. And if the RNNT search algorithm, which is used during the training, there is some recursion over these alpha betas, like in the forward-backward algorithm, you would see something similar. Because if it searches fewer like token IDs, the memory consumption drops dramatically. So instead of 10 gigabytes, it needs 2.5. So this is this optimized transducer. That's one functions implementation of our RNNT, and this pruned RNNT is the one which is used widely. Again, the water rate results are about the same, and the memory consumption is dramatically smaller, and also it's faster to evaluate. Yeah, and if we have transducer systems and CTC systems, why shouldn't we combine them? That it can regularize the model to learn the encoder something more, try to avoid overfitting also. So it's just combining these two systems. So into transducer, there is CTC head and loss edit, and that's it. And there comes the quite recent paper, CRCTC, which is the consistency regularization on CTC. And the idea is, it's surprisingly simple, but it's efficient to reduce the overfitting. And in the experiments, I have seen that there was this pruned loss, which at the beginning the loss was dropping and then started increasing. And after starting to use this, it just disappeared, this overfitting trend on the validation data. And so what it does, at the beginning there is one utterance, and it's processed by spec augment 2 times. And each time, like, different portions are masked. There is the time masking, there is frequency masking. In spec augment, there is also some warping. It's like processing to the images to slightly like adjust, shift a little bit, do some distortion on the spectrogram seen as image. And it's each time it's processed differently, so different parts are masked, but it's processed by the same encoder. The CTC outputs are obtained. So there are two sets of CTC posteriors, and it's possible to compare them. And because it comes from the same utterance, there should be same posteriors. So this CRCTC, it adds a loss function, which is applied this symmetric Kullak-Leibler distance on these two CTC outputs, so it's actively pushing them to be as similar as possible. And so this regularizes the system. And even for us, if we are interested in the transducer, ASR, and this happens on the CTC, indirectly it helps to improve the generalizations. I saw like, let's say 1.5 better water rates because of adding this. It's one model, yeah.
So you make many powers and then compare the output?
It's like, yeah, it's one model, and it's like, yeah, two sets of data which are forwarded. So, yeah.
Are those augmentations like connected where like if you're cutting out one part, you're not going to be doing the same thing to the other part? Like that way you're not just missing a whole chunk in the whole audio?
Oh, it's more like, it's randomly selected where which parts will be masked. So yeah, and it's quite unlikely that the same parts would be masked out. Well, yeah, it's better never say never. Still, there could be some parts masked in both versions, but yeah, there is no communication between that. In version A, this was masked, so therefore in B, this should not be masked. It's not implemented in that way. It's just having it's stochastically happening, the masking.
Yeah, how is the library extrapolate like the representation space?
Sorry.
How is the library like Kullak-Leibler library extrapolating the representation space? Is it like you assume that they belong to a family?
Oh, it's what I can say. It's taking the PyTorch KL distance implementation, and this one is symmetric. Normally, the KL distance is asymmetric. That one is like the reference, and other is the target, and the way it's implemented.
The question was, it is calculated, I assume, on top of the probabilities.
Oh, for the probabilities, yes. Yeah.
But like spreading probabilities, so calculate the distributions spreading frame by frame distribution of the total outputs. They assume that they are proportional. No, the CTC outputs. Oh, algorithm distribution. Okay.
Yeah, and to precise more, it's because KL distance is asymmetric, it's computed twice with the arguments flipped, and there is, I think, 0.5 on both as a scalar. And tokenizer, this is more like standard thing, most likely. There's the sentence piece from Google. There are 500 tokens, which empirically I tried to increase. I didn't get improvements given the data we have. And it's the unigram token type, which means that it's like a mixture of 3 types of elements. It's the graphemes, some word piece units, and whole words, those which are very frequent, they get into the. And it's trained on the text data for training the ASR. So this example, how it works, so tokenizer, there is some sentence. I have an idea. Just note here that this punctuation is as separate tokens, separated by white space. And the tokenizer just translates it into a series of integers. These correspond to neural network outputs. So there are like the joiner output dimensionality is 500. And it's possible to back translate these numeric values into the actual tokens stored somewhere in the table. Okay. And so we have the encoders, we have the training losses, we have the tokenizer, some training data, so we can do the fine-tuning.
But the tokenizer, does it introduce data bias? Because there will be, like, I think it uses some statistics to...
It's, yeah, what I did was I took the, took the training data for fine-tuning data for the ASR. So there should be domain bias by this training data. I'm aware that if the ASR should be generic, it would be wiser to collect some large text database and train the tokenizer on this to cover well the language. I had seen that, especially for OOVs, it was for new words not seen during training, the ASR system has trouble recovering them correctly. Yeah, so we have the EU ASR data, train dev test, separated, common voice, Vox Populi. In total, there is around 300 hours for Czech, Estonian, and English for fine-tuning. And these are the results. So ZipFormer, this is trained from scratch, from random initialization. Just there are these stabilizing modules like this balancer, whitener, etc. And eBranch former was pre-trained on this 300,000 hours by BestRQ on the Vox Populi data, and it's also like 3 times bigger model. Well, the latency is the same. That here we assume that it's streaming ASR, the chunk size is the same, the left context size is the same. And ZipFormer was like around 1% having better results. And to put some more info on this, just like Igor was showing, we have for us the word error rate means calculating distance on top of words which include true casing for like proper nouns and punctuation as like standalone tokens. And if we strip that off, we get this mapped where, which is in the parentheses. Yeah, and this is the slide I spoiled earlier that we were wondering, okay, we would like to show that the pre-trained models are better for like small amounts of training data. Well, yeah, I did not try to go lower than 5 hours, but even with 5 hours for ZipFormer, I was getting word error rate 40% on Czech. And in this case, the tokenizer, instead of 500 units, there were 250, because it was already too many units for the last. But it's quite nice how it looks. Given the steps, yeah, the steps are more like doubling the previous. So it's logarithmic. It follows the nearly linear trends to decrease the learning rate in terms of word error rate. The word error rate. Yeah. So up to now, this was the comparison of like whether to pre-train or not, and given our like specific set of models. Now I'd like to speak about streaming ASR. That, intuitively, there is some speech. It gets chunked into pieces. It goes through ASR, and we would like to get some output from the ASR as soon as possible so that then some, let's say, NLP module can build upon. Or so these chunks, well, for streaming ASR, the latency should be taken care of. If it's like more than 1 second, it might be already too much. So we were trying few values of chunk size and left context size, and this seemed as like a relatively good compromise so that the latency is still reasonable. So there is 540 millisecond chunk size and roughly 2.5 second left context added to it. Yeah, without using any left context, the word error rate, instead of 10%, it worsens to 40%. It just doesn't work. You really need to have this left context inside. And yeah, streaming ASR also needs causal processing. So because it's streaming, we cannot see in the future, and we need to process the signals accordingly. And if you would continue this way, there is some speech, there are some outputs of ASR. There is some state of the decoder, and the hypothesis gets longer and longer. And at some point, the streaming ASR needs to put an endpoint. It needs to realize that, let's say, a phrase has ended or utterance has ended, and that it can like reset its internal states, and it can stop like sending out the partial output. And this is in the endpoint where this happens. From the user experience perspective, it restarts the decoder output, the endpoint. For downstream application, it can be an interesting spot that after reaching the endpoint, it's clear that the ASR output will not change anymore. So it can be sent to an NLP module. And the way it's implemented in a Sherpa, well, it follows from what was in Kaldi. So in Sherpa, there are three rules. Basically, it's after having some silence, the endpoint is triggered. So if there is silence, most likely it will not continue into speech, and we can put endpoint and restart the decoder. If there was speech, this timeout decreases to 1.2 seconds. So if there was some speech and there is a short pause, yeah, we want to avoid the situation that there is like infinite speech and this buffer with the partial output would grow infinitely. So it decreases this threshold to 1.2 seconds. And there is also this security rule that when the utterance length reaches 20 seconds, it just cuts off no matter what. In the middle of the word, it can happen. The previous two symbols still are passed to the next segment, but it can put like endpoint in the middle of the word. It's still okay, and I had seen it happening, and not like, yeah, how to say. It's not a bad thing. It's more like to use the resources optimally, and it does not make the results bad, because in the middle of the word, if it knows the previous outputs, it still can predict the next symbol correctly. Okay.
How did you settle on those, or I don't know, how were those rules set? Like, is it just a coincidence that those are like, what, four chunk sizes and two chunk sizes for rule 1 and rule 2? Or did you guys settle on that, like, just fine-tuning?
Well, it's possible to adjust it, but these are the default parameters, and it should, well, yeah. Somebody was implementing it and was playing with it and found out that this works more or less good. But yeah, if there is the endpoint, because if there is endpoint in the middle of the word and it can still continue correctly, it doesn't matter much if there was endpoint or not. It's just in beam search decoder, there are several active tokens, which each can continue in like several more continuations. And at the spot of the endpoint, this decoder state, just the best path is taken, it's fixed, finalized, and only this path is the seed for the continuation of the decoding. That's the only limitation which comes from it, but still it can continue correctly. So from the user perspective, it doesn't change much, but that's... Okay. Yeah. So we had the eBranch former encoder. Originally, it was not for streaming, it was for batch processing. And so what Alex did, so we could pre-train it in a causal way. There were two modifications necessary. That first is masking out the future. So this triangle over here. So this is, those are the attention weights from the attention mechanism, example of it. The way it works, so there is some, on this axis, there are the inputs. On this axis, there are the outputs. So let's say for this slice of the frame 50, this is logarithm, so the numbers are minus something values. So at this slice, the output is composed of all these frames given the values on this line as a linear combination of the inputs from this value matrix. And if it was non-causal, there would be also allowed to see the full box over here. Because it's causal, this upper triangle is just masked out, is inaccessible by the attention mechanism already in the pre-training. And the second thing was there are these point-wise convolutions over time axis. So originally, they were looking both in the past and in the future. So if you implement 1D convolution, you can just have the input matrix, put zero padding in the past, zero padding into the future, half the length of the filter, and that's it. It looks both in the past and in the future. And if you just discard zero padding for the future and increase the zero padding for the left part, still the number of frames on the output will be the same, but it will stop looking into the future because there is no padding on the right side. So that's, yeah. In our case, we kept the length of the filter. It should be possible to also use 16 instead of 31. We were trying this too. The results were more or less the same, but that's what we did. And then the rest of the pre-training was the same as for the non-causal, pretty much. For the fine-tuning, pre-training was happening with the transformers code base, whereas fine-tuning is already happening with K2 icefall. And this was the original mask. The future was inaccessible. And for fine-tuning, there is the stairway attention mask. So here we can like slightly relax it. We can allow to attend to the future within the chunk for the streaming ASR. And there is it's also allowed to attend to the history inside of the left context of the current frame. But the length is limited. It's this 2.5 seconds, roughly speaking. So for the whole utterance, it looks like this, the attention mask being used. And in more detail, this is the situation that there is the current chunk over here. It's passing the main diagonal, which is also the original line of causality from the pre-training. And next to the current chunk, there is also the left context accessible. So these are the only frames that the attention mechanism has access to during the fine-tuning. In the practical implementation, there was a list of chunk sizes and list of left contexts, and there was stochastic selection of those parameters. It was, for each batch, one of those was selected randomly. And the -1 is like not limiting. It equals to like having unlimited chunk size. So then the history would be unlimited. But still there was the causal mask, so which was slightly shifted to the future, just to this edge, so that it does not change all that much compared to the streaming ASR. But that's, yeah, I heard in some companies they are using it as well. And I tried to use just this target preset of 64-56, and I got worse results, not much, it was some 0.5% water rate, let's say. So if it's randomly selecting from the list, it's better result, water rate, and in the same time, the model supports several presets. So we can deploy it in with several configurations if you wish to. That's yeah, second benefit. Yeah, next there is the attention mechanism. So we have this left context. So how the hell should we put it into the self-attention mechanism? So this is the formula for self-attention. This is how it's visualized. So at the beginning we have X, the input, that's used for queries, keys, and values. So there are these linear transforms on top of X applied. So we have this matrix QKV. This is the QKV over here. And to the key matrix, there is the left context, which is padded in the history. And to the V matrix, there is this left context, which is padded to the history. And the formula, the rest stays the same, just concatenation of matrices over here, as shown on this line. And that's it. Then there is the query, which comes into the formula. It's the chunk itself. It's this like 16 frames of some signals. And it goes through all this, through the whole formula. And on the output, there is, again, some matrix with 16 lines, with 16 frames. That's it. Job done. Just some extra information is added there that the encoder, the attention mechanism, can attend to this left context and use it for computing the attention weights, and also can use it as like input for this linear combination of embeddings from this V matrix for the output. Okay. One more thing, there are these 1D convolutions used for the pointwise convolution. And also, if the chunk comes, there is some left context of the history. We cannot use zero padding for each chunk. It would like create some artifact inside the forward. Everything should look just as if we processed the whole utterance in the same time. That's the goal. So there is the left context for the convolution. So there is the input chunk, there is some convolution filter. Again, the input chunk gets extended by the left context by simple concatenation. Convolution is computed, there is some Y. X and Y, same length of inputs on the time scale. Again, job done. There are 700 channels like this. Each is processed independently, and that's what's in the code. So these are the two things, the attention mechanism and this 1D convolutions for this left padding. Yeah, sorry, I didn't emphasize this stairway attention mask. This applies to the fine-tuning. So the fine-tuning for the whole batch composed of utterances, single forward call and backward is for the whole batch. Whereas this is already inference. Inference is chunk-wise, and each chunk has like 16 frames for this 640. Well, it depends. It's different for zip former, different for e-branch former, but yeah, the step size. Yeah, so this is for inference, this left context padding for attentions and for the 1D convolution. And this convolution, yeah, as I was speaking about the e-branch formula, is there twice. One is this local extractor, and second, where it's multiplicative, and second times it's in this joiner network where it's additive. But the padding is done in the same way. So from the code point of view, this is a forward through one encoder layer. So you can see that the caches are part of the API in the PyTorch. The input is the X, is this hidden states, and the caches for the keys values and the two convolutions. It's here. And if there is some client calling in and there's ASR running for him, he has some representation, some online stream, which has his outputs and the state of the stream of these attentions and convolutions represented there. And to make the system efficient, there can be several clients, and their inputs are batched together, the states are batched together and are forwarded through the neural network in one call for several clients in parallel. This is very beneficial, especially on GPUs. It's much faster than on CPU. For CPU, it can be like per single client, and having it multi-threaded, there's no much difference in performance. But for GPUs, it's very, very much better. Yeah, and last thing to cover for inference for the streaming ASR. So there is this pre-encoder inside the system, and the pre-encoder, it uses 2D convolutions inside of it. And this can be with and without zero padding on the time axis. And because we need to, in the inference streaming, it should look the same as during the fine-tuning. We needed to introduce their 6-frame overlap of these F-banks. And I will show it why. It's on the next slide. So if we have two 2D convolutions, these are the parameters. So there is kernel 3 by 3 for the first layer, for the second layer. There is zero temporal padding. There is one like frequency axis padding for both first and second. There is striding also. So this is how the situation looks. So at the beginning, we have this time series of frames of these F-banks. And so from these 15 inputs, there are these 3 outputs being computed. And you can see that, let's say for number 1 output, this is the interval of inputs which is used in this computation tree. And there is this branch which is shared between the neighbors. Yeah, there's some kernel size, some striding visualized here. And you can think of it, it does not matter much how big the chunk is. Always there will be some first frame and last frame. And for the first frame, these 3 frames will be shared with the previous chunks. And for the last frame, these 3 will be shared with the ongoing chunk. So that's why this 6 FBank overlap. Yeah, so that's the end of the streaming. Those were some like low-level thingies, how it's implemented and how it works. Now, just for the deployment, this is nowadays it's mostly the ONNX is used for deploying. So it's like some special language for representing neural networks. The things to remember is that ONNX models cannot be trained easily. So once converting to ONNX, it's usually not possible to train this model. It's possible to reverse engineer to some extent, but it's not always reliable. And the original PyTorch code with forward functions, it cannot be restored from this ONNX. Maybe generated something similar, but not exactly one-to-one. At least that's my belief. So ONNX, it's again similar to PyTorch. Yeah, there are some variables and some computation graph. There are some libraries like ONNX runtime from Microsoft, which can be used to do the inference with the models on CPUs or GPUs. Yeah, inside of the ONNX model, after exporting, there is a way to put there some metadata. So here it was used to mostly, because we have this keys and values and this convolution left contexts. These are the inputs of the neural network. So it's the chunk of the FBanks. But also these state buffers, which are there's something like 70 different inputs of the neural network coming in during the streaming ASR, and only one of it is this input FBank. Others are these state buffers. So, and to know properly what the dimensions should there be. So at the beginning there are some initialization, some zero matrices, and then the buffers they need to the C++ code needs to know what the dimensions should there be for these buffers so that it can add them as these inputs. Yeah, so there is this, for the convolutions, what the dimensionalities there are. Yeah, this is, this is the chunk size. This is the chunk size including the overlap on the input, what's the size of the left context len, but already in the embedding times, not the original FBank times. And number of eBranch former layers inside, some dimension. Okay, so some metadata, that's it. Yeah, one thing I learned on the way was there are 2 spots where problems can occur. That one is that while exporting the model, this can fail. If there is some function which is not supported, not representable in ONNX, it will just crash, and it's your job to fix it, to find some workaround. And second is even if the model is exported, it does not mean that it will work. That there can be still some dimensionality mismatch inside of the model, which the exporter just didn't complain about, but the ONNX runtime can crash and tell at the node of this name there is some error occurring. And for this case, there is some Neutron website that it's possible to upload there the model. Okay, so yeah, okay, this works. Yeah. Yeah, so there is this Neutron application which can be, I'll reduce the volume a bit, which can show graphs like this, and you can explore the modules. There are some more data for each node. Yeah, sorry, I just, how to say, transpose the image so it fits into the slide. Otherwise, it would be in the normal on the website. But yeah, so if the ONNX runtime crashes, it gives some node ID, and but this was not really helpful on its own. What was helpful was to like remove some parts of the network and check if it still crashes. And I ended up using, like, introducing some dummy computation in the forward function, like this exponent by the power of close to 1, let's say, and having several of those with different numbers in it, so I could like see which is where. And then I was looking in the graph where this power appeared, and by seeing that between these two power calls the problem was, I could see it in the original code. Where should I focus and fix the original code? There was some bug in the transformers library which was fixed meanwhile, but I didn't know about it. I was using still the old library, so yeah, this helped me a lot. Okay, so this is about these ONNX models, and next is the Sherpa ONNX. This is like deployment library for ASR or for speech applications in general. So links are here, the code, documentation. Yeah, you can just pip install it if you need it, and you don't need to develop. So it's like applicable as a client server for streaming ASR. It can serve several clients in the same time, both on CPU computing or on GPU, and it's built around the ONNX runtime C++ library from Microsoft. So the good thing is, like, why to use Sherpa ONNX, that yeah, if you have some torch model and you would like to deliver it, most likely for some products, C++ code is better than Python to like integrate it. And also the PyTorch, well, the installation, I think with GPU support, it takes 2 gigabytes, even more. And with the Sherpa ONNX, it's some like 6 megabytes, the library. So it leads to much lighter deployment, to like avoid using PyTorch for deployment and base it on Sherpa ONNX. And also no K2 code is needed for the delivery, that everything is already inside Sherpa ONNX. And there are some slides from tutorial with more details. Just for the API example, it's a C++ library, but it has bindings to Python through this PyBind 11. Yeah, in the C++ level, it looks like uglish. These interfaces being coded, but from Python it looks already quite neat. So this is example for one client that at the beginning there is instance of the recognizer. There is this from transducer which instantiates the recognizer, loads the models. Then from the recognizer there is the create stream. So these are the data related to single client inside this variable S. And then given that we have some audio generator which is giving the chunks of audio, these are given by this accept waveform into this decode stream. This is where feature extraction is happening, this fbanks. And next, there is, the recognizer asks the stream if it has some new data. And if it does, the recognizer decodes next chunk. There will be some output to display, and if there is some endpoint occurs, this is just when this reset is called. This means that the endpoint was done. If it's detected and ignored, it would just continue without the reset, but just this reset actually does what should happen at the endpoint. Yeah, so not so complicated to work with. Concerning the model support for online ASR, there is ZipFormer 2, which we were using, eBranch former that was introduced there. There is also older ZipFormer, Conformer, LSTM. For offline ASR, there are other models like Whisper, that's quite popular. There are Nemo models, VNet models, something called Moonshine. But it's not limited just to ASR. There is also text-to-speech diarization, punctuation, keyboard spotting, but done by ASR. There is also, I think, speaker ID was there. That's, I didn't use those, I just saw it's there, so sharing the info. And the strong side is the interoperability. So it's a C++ library, which is industry ready. As I've said, for us, there was Python interface to be used, but there are also examples for other languages. So there is iOS, Swift support, there is Android, Harmony OS, so mobile devices are supported. I don't have experience to try it myself, but it should be ready for this. Also, Windows is supported. That's, in the old times of Kaldi, Windows was important because then we worked for Microsoft. WebAssembly also, this can be now handy, this interpretable code by the browsers. So there's the documentation link for more details. And there are these ASR-ish features. I looked in the past a little bit, but not using them now. There is support for shallow fusion, which could be used to tweak a little bit, steer the model towards some new domain, but it's not so efficient as it was in the Kaldi time. And there is boosting by a list of hot phrases, so there is a way to suggest what are some special words which could appear in the ASR, and then the search would give them some score discounts to make them more likely to appear on the output. Yeah, and for the runtime, we used Sherpa ONNX as some core ASR library, but around it, there's the whole infrastructure. So again, it's client server. There is some external API for the client, which is either with this gRPC, that's some, I don't know if you've heard of, or it's some, let's say, there is some meta language for describing the message formats, and this gRPC can be used to generate code for binding to C++, to many different languages, basically. So it's possible to combine the technologies, and it will just synthesize the code as a library for you, and then use it as some communication module, and it supports also an SSL encryption. So it's in the industry, it's quite standardish thing to be used, this gRPC. And WebSockets, I think that was for the web application, that the web application did not support gRPC, so we had this proxy using WebSockets so that the web browser application can connect to WebSocket, which then connects to gRPC internally, and then, well, yeah, so there can be many clients served in the same time. The online stream, it contains this state buffers, the decoder state, these active tokens being there, and the partial results. Yeah, there's this batching of chunks for accelerating. Yeah, and there are two like supported ways that either it's a stream, let's say from microphone, which is coming in and the transcripts go out, or there is upload for a file, which is another use case for, let's say, for some like, translation they need to first have some captions so they can then take the recognized text and process it. Yeah, so that's the internal structure of the server. That there's the ASR over here, but there is like some ASR output post-processing here. This is for converting the output format of the ASR output. Yeah, this is this like entry point communication module, and this is to convert the format of the input. That's, yeah. Yeah, and it can run on the host machine or inside Docker. There can be also like several Docker instances in parallel, and there was some like example using Nginx to load balancing between them. But this is already like application. It could be like interesting to look into, but still for completion putting it here, but maybe for PhD student it's not that relevant yet maybe. So yeah, that's it. Yeah.
Overshadowing. Any questions? Just have one question. You mentioned that you are using Onyx runtime.
Mm-hmm.
So I was wondering if, as your models are building above PyTorch, why do you? So have you tried to use this PyTorch framework to make inference on like for deployment, because they have this executor framework just to make inference? Do you know if, because I know that there are some problems related with the operators.
Mm-hmm.
If some operators are not implemented in Onyx runtime, then you might have to implement them or just try a different model. But
to be honest, I used this because it existed already, and it seemed like quite possible to use this and quite mature. But yeah, that's true that for PyTorch, I think there was this torch script language which could be used to represent the models, and then there are some, it should, it's maybe this torch script based servers are older than the Sherpa on NX. Sherpa on NX is quite new. It's like, it started maybe some 3 years ago. Was it implemented? And then
how is the approach when there is no operator supported in Onyx? You just change the model, or?
It's like, I think in my case I had to disable the balancers because it contains some like this operation which was not allowed, but balancer is important only during training, so that was fine. While debugging the export to ONNX, at some point I was thinking that I have to convert the whole model to make it compatible with torch script. but then I ended up rewriting many different spots which were necessary for the torch script, but which were still okay for this ONNX export. So maybe this ONNX is like stronger in terms of representing neural networks compared to torch script. Yeah, I saw it in the documentation of Sherpa ONNX that it exists, but I did not, yeah, I don't know the details. Or.
I don't know enough to tell you what the differences are, so it should be better.
Yeah, yeah. No.
So if nothing, I think it's time to close the first day. Well, thanks all the speakers. And we will have the summer school welcome picnic, but only we ended up a little bit earlier. So the picnic should be ready at 5:30 or something like that, here, just in front of this lecture room. So I think it would be nice time to have like a 1.5 hour walk or relaxation in the grass. Beware of ticks, of course. And or stroll around, or sitting, doing your stuff, whatever you want. So let's gather here at 5:30. And thank you very much for surviving the first day. And see you at the picnic and tomorrow at whatever, 8 bus, 8:15 here. Thanks.